The granite in the Great Pyramid, if you look at the famous King's Chamber, its walls and its roof are, the ceiling of the King's Chamber are all made with gigantic granite blocks.
I'm more interested not in how the Egyptians built the pyramids, but how the pyramids helped to build Egypt.
What if everything you've been told about how the ancient Egyptians cut granite is wrong? For more than a century, historians believed the mystery had already been solved. Copper tools, stone hammers, patience, and thousands of workers. Case closed. But when researchers fed microscopic cutting marks from Egypt's hardest granite into Grok AI, they expected the system to confirm the accepted explanation. It didn't. Instead, the AI produced an analysis that challenged one of archaeology's oldest assumptions. According to its calculations, the precision visible in many granite cuts doesn't fully match the methods traditionally used to explain them. If that conclusion is even partly correct, one of history's greatest engineering mysteries may need to be re-examined. But before we reveal what Grok discovered, hit like and subscribe. You won't want to miss what's coming next. Now picture yourself standing inside an ancient Egyptian quarry, running your hand across perfectly curved grooves carved into one of the hardest stones on Earth. These aren't random marks. They're smooth, deliberate, and remarkably consistent. The closer researchers examined them, the more difficult they became to explain. By the end of this video, you'll understand why a single AI analysis has reignited one of the most controversial debates in Egyptology. The theory everyone was taught for generations. The accepted explanation has been straightforward. Ancient Egyptian builders relied on manpower and dolerite, an extremely hard stone shaped into heavy pounding tools. Workers repeatedly struck the granite until the desired shape slowly emerged. No one questions the enormous effort this would have required. Historians describe large teams working in relentless desert conditions for months to free a single block from the bedrock. Given enough workers and enough time, the process appears entirely possible, but possibility isn't the same as proof. To test the theory, researchers recreated dolerite pounders using the same materials and dimensions described in historical studies. They then attempted to reproduce the marks found in Egyptian quarries by striking granite exactly as the traditional model suggests. The results were nothing like the ancient stone. Their test surfaces were irregular. Some blows dug deep, while others barely marked the granite. Spacing varied, edges chipped unpredictably, and repeated impacts produced rough, inconsistent patterns. As fatigue set in, accuracy declined even further, a completely natural result of prolonged physical labor. The ancient quarry marks tell a very different story. They display long, sweeping grooves with strikingly uniform depth and spacing. Instead of irregular impacts and scattered fractures, the surfaces show a level of consistency that proved extremely difficult to reproduce in controlled experiments. That growing gap between experiment and evidence is what convinced researchers to stop debating assumptions and let Grok AI analyze the patterns without any attachment to the traditional explanation. Handing the mystery to a machine. Here's the thing about human experts. They walk into these sites already believing something. They've read the same books, sat through the same lectures, absorbed the same assumptions. So when they look at ancient tool marks, they're primed to see what they expect. A hammer story produces hammer conclusions. An AI doesn't carry that baggage. It doesn't know what answer it's supposed to find. It just measures. The process started with photogrammetry. Thousands of overlapping high-resolution photographs stitched together into a precise digital twin of the quarry surfaces. Every groove, every curve, every microscopic irregularity captured and rendered in 3 dimensions, rotatable, zoomable, measurable, down to fractions of a millimeter. That entire data set went into Grok AI with one condition: no context. The system wasn't told this was Egypt, wasn't told what era it came from, wasn't told what tools historians assumed were used. It was simply asked to measure the geometry of the marks and compare them against a vast internal library of tool signatures, ancient hand tools, medieval implements, and modern industrial equipment alike. The scale of the analysis alone is hard to picture. Hundreds of individual cuts scattered across multiple sections of the quarry, each one broken down into its curve radius, its entry angle, its depth, and its spacing, relative to its neighbors. Work that would take a human research team years to complete by hand. The system worked through methodically, without fatigue, without opinion, and without wanting a particular outcome. Then the numbers came back, and one figure sat above everything else on the report. The total variation across every single cut, measured site-wide, came in barely above the margin of measurement error itself. To understand why that number stopped the room, you need a reference point. Even a highly skilled craftsman working by hand today, using excellent modern tools, will show noticeable drift from one motion to the next, a shift here, a slight change of pressure there. That's not sloppiness. That's just what a human body does. Variation in that range is considered completely unremarkable. What the AI found instead was consistency so tight it barely resembled human output at all. Not one section of the quarry, not one lucky craftsman having a good week. The entire surveyed area behaving almost like the product of a single repeating mechanism. That's when the conversation in that research room stopped being about archaeology and started being about engineering. The search for a match. Once the geometry was measured, the next question was obvious. What tool actually produces marks like this? The system started where you'd expect, testing the marks against the pounding stone theory one more time, just to be thorough. Same result as the physical experiment. Hammer strikes are irregular by nature. Depth varies, angles drift. Spacing is never perfectly even, because no human hand can repeat a motion with mechanical precision thousands of times in a row. That theory failed again, cleanly and immediately. So the system widened its search into modern tooling, and 3 candidates rose to the top almost immediately. The first, rotary cutting tools fitted with an extremely hard, abrasive edge, spinning at speed to slice cleanly through dense stone, leaving behind smooth, continuous lines. The second, pressurized cutting systems that use a concentrated stream of liquid, mixed with fine abrasive particles, prized in modern stonework for how controllable and consistent the resulting cuts are. The third, and arguably the strangest fit, vibration-based cutting, where a blade oscillates at extremely high frequency, allowing it to work through hard material with almost surgical precision. None of these tools share sharpness as their defining trait. What they share is repeatability. A spinning blade doesn't get tired on its 400th pass. It doesn't loosen its grip. It doesn't drift half a degree because the operator's arm is aching. It performs the 400th cut exactly the way it performed the first. That mechanical sameness, not sharpness, not strength, is the real fingerprint separating a hand tool from a machine. And that fingerprint is exactly what kept showing up, cut after cut, across the quarry. When Grok AI finished ranking its matches, one category of modern industrial process rose clearly above the rest, with a confidence level in the low to mid-90s, high enough that the researchers reportedly went back and re-ran the analysis twice, assuming something in the dataset had to be wrong. It wasn't. And there was a second detail buried in the same report that made things worse. Across dozens of separate cuts, spread across different areas of the site, the angle at which the tool met the stone varied by less than a couple of degrees. Holding that level of angular consistency by hand across a large working area over an extended period isn't just difficult. Most craftsmen would call it functionally impossible. On one side of this argument stands 100 years of settled history. On the other stands a machine with no incentive to lie, describing something that behaves like a controlled industrial process. That gap between the two positions is the entire mystery in a single sentence, and it's about to get a lot harder to explain away. It's worth pausing here on what the researchers actually did next, because this is the part that separates a real investigation from a viral claim. They didn't stop at one pass of the data. They deliberately tried to break their own result. They removed a portion of the data set and reran the comparison, checking whether the match held up on a smaller sample. It did. They swapped in a different reference library of tool signatures, one built from an entirely separate archive of historical and modern cutting equipment, just to see if the same conclusion would survive a change of source material. It did that too. Each time they tried to poke a hole in the finding, the same category of process kept rising back to the top of the list. That kind of stress testing matters, because a single run of any analysis can be an artifact of how the data was framed. A result that survives being challenged from multiple directions starts to look less like a fluke and more like something worth taking seriously, however uncomfortable the implications happen to be. The shafts that shouldn't exist. This next part is the detail almost nobody talks about, and it's the one that should genuinely unsettle you. Scattered through the site are narrow vertical shafts plunging deep into the bedrock, some barely wide enough for a single person to stand inside comfortably. Tight, dark, claustrophobic spaces, cut straight down through solid granite. From the surface, they look unremarkable, just holes. But climb down and examine the walls, and the picture shifts immediately. The exact same curved, evenly spaced marks found across the open quarry above are also present down here. Same depth, same rhythm, same eerie consistency. And that consistency is the problem. Think through the mechanics honestly. If the accepted theory is correct, heavy stone pounders, swung by hand, then the person doing the work needs room, real room. Enough clearance to draw the tool back and generate the momentum required to actually damage granite. Take away that swing radius, and you take away the force behind the blow entirely. A pounder resting gently against granite with no run-up accomplishes almost nothing. The entire hammer theory lives or dies on having space to swing. These shafts don't have that space, not close to it. So when researchers fed the shaft dimensions into the AI system, width, depth, required swing clearance for a pounding tool of the size historians describe, it returned a conclusion that pushed the debate somewhere nobody particularly wanted it to go. It classified a hand-swung pounding method in this environment as physically impossible, given the spatial constraints involved. Not unlikely, not difficult, impossible. But here's the unsettling flip side. The system also modeled what kind of process could produce these marks in a space this tight, and found that a tool applying direct downward or forward pressure, with no backswing required at all, could realistically produce identical results even in the narrowest sections of the shaft, which means the one tool the mainstream story insists was used couldn't have physically operated in the exact place where the evidence says the work happened. Sit with that for a second, because it's not a small inconsistency. It's a structural crack running straight through the foundation of the accepted explanation. What the microscope found. Everything up to this point came from the surface. The next layer of evidence came from going underneath it. When you strike dense stone repeatedly, the impact doesn't stay neatly on the surface. It travels. Internal crystal structures fracture in unpredictable directions. Tiny fissures spread beneath the point of contact, and the surrounding material becomes visibly stressed. Under magnification, hammered granite looks chaotic, a landscape of splinters and micro cracks radiating outward. The quarry marks show almost none of that. Under the lens, researchers found something closer to a clean separation than a violent impact. What specialists refer to as a shear boundary, a sharp, deliberate line between the worked surface and the untouched stone beside it, with minimal disruption extending into the material below. It doesn't look like something that was struck. It looks like something that was carefully, precisely divided. Then came the finer details. Extremely subtle, rotational striations appeared under closer magnification. Faint curved lines, suggesting a spinning contact point, had passed across the surface while rotating steadily in one direction. Samples, pulled from entirely different sections of the site, showed the same rotational signature, running the same way. Alongside that, researchers documented small zones of concentrated heat exposure directly on the cut surfaces, not the broad, diffuse heat you'd expect from two rocks grinding against each other, but tightly localized thermal marks, consistent with friction, generated by a fast-moving, narrow contact point. And finally, microscopic traces of an extremely hard abrasive mineral were recovered from within some of the cuts, along with unusual carbon formations that several analysts described as resembling structures found in modern industrial cutting compounds. Taken individually, any one of these findings might be dismissed as coincidence or contamination. Stacked together, the clean shear lines, the rotational striations, the localized heat, the hard abrasive residue, they stop looking like isolated anomalies and start looking like a coherent description of a process. When the full data set went into Grok AI as a single combined analysis, the conclusion aligned uncomfortably well with everything found on the surface. Not hammer damage, not the signature of any hand tool in its historical database. The closest match, according to the system, was a controlled abrasive cutting process, something we would today describe as industrial in nature. Under the microscope, this stone wasn't broken, it was machined. There's a secondary detail from this stage of the investigation that rarely gets mentioned, and it deserves more attention than it gets. Researchers also examined the tiny fragments of debris recovered from inside the cut channels themselves, the leftover material that would have fallen away as the cut was being made. In hammered stone, that debris is typically a chaotic mix of particle sizes, large chunks, next to fine dust, with nothing consistent between them, because every strike breaks the material differently. The debris recovered from these cuts told a different story. The particle sizes clustered tightly around a narrow, repeating range, almost as if the material had been removed in uniform layers rather than knocked loose in random impacts. That's not a detail you'd expect to find by accident, and it's not something a hammer, however skillfully wielded, tends to produce. It's the kind of signature you'd expect from a process that removes material in a controlled, repeatable way, cut after cut after cut. The timeline that runs backward. If everything so far felt strange, this next part is where the ground genuinely shifts. Scattered across parts of the site are old painted markings applied directly over sections of the cut stone. That layering matters enormously because it tells you the order events happened in. The stone was cut first. Only afterward, sometime later, did someone come along and paint over it. When researchers attempted to date those paintings, the estimates placed them significantly earlier than the commonly cited start of organized dynastic civilization in the region. And if the paintings are that old, the cuts underneath them have to be older still, pushing the origin of this technique back into a period most historians associate with small, scattered groups equipped with only the most basic tools imaginable. Here's where it gets genuinely difficult to process. Researchers asked the AI to compare the precision of individual cuts against their estimated age, essentially mapping skill level across time. The relationship that came back ran in the opposite direction from everything we'd expect. The oldest cuts in the dataset were the most refined, the most consistent, the most mechanically precise. As the timeline moved forward, toward eras historians consider more developed, the quality of the cuts actually declined. Rougher edges, more irregular spacing, more of the ordinary signs of human hand tool work. Every civilization we have solid records of follows the same basic arc. Early work is rough. Later work improves as knowledge accumulates and techniques get refined. This site tells the opposite story. The earliest work is the best work. Whatever skill produced, it appears to fade, not grow, as time moves forward, which leaves an uncomfortable question hanging in the air. What if the people at the very beginning of this timeline already possess something that later generations simply lost? Reading the stone from the outside. There's one more layer to this, and it might be the strangest piece of the entire puzzle. Granite isn't uniform on the inside. Running through it are bands of different minerals, harder pockets, and natural weak seams, where the material will separate more easily than everywhere else. Modern quarry operations spend real money locating these internal features: sonar equipment, geological surveys, computer modeling, specifically so they can plan cuts along the path of least resistance instead of fighting the stone's natural structure. When researchers mapped the internal mineral composition of several blocks and compared it against where the ancient cuts actually run, they found something that shouldn't be possible without that kind of modern equipment. Many of the oldest cuts follow those exact same internal weak seams, as if whoever made them already knew where the stone would yield most easily, despite having no way to see beneath the surface. That's not a small coincidence. The outside of a solid granite block reveals almost nothing about what's happening a foot below the surface. You need specialized tools to see that structure today, to consistently land on the path of least resistance. Without them, over and over, across many different blocks, isn't the kind of thing that happens by chance a few dozen times in a row. When this data went through Grok AI, the system flagged a genuine statistical relationship between internal stone structure and cutting paths, with a confidence level in the high 80s. The report described it plainly. The cuts appear to have been planned according to structure hidden beneath the surface. Some researchers have started referring to this, only half-jokingly, as evidence that whoever did this work had some method of understanding a stone's hidden architecture before ever touching it. And if that's true, the next question writes itself. If they were capable of all this, why is there a 1,000-ton monument sitting abandoned in the middle of the site, never finished? The unfinished giant, and a pattern that won't stay local. There's a single object here that stops nearly everyone in their tracks the moment they see it. Still attached to the bedrock, where it was originally carved, lies an enormous, unfinished monolith. By some estimates, had it been completed, among the largest single stone objects ever attempted. The official explanation is straightforward. A large crack developed partway through the work, and the project was abandoned as a loss. It's a reasonable explanation. It just doesn't match what's actually carved into the stone. Cutting marks continue well past the point where that crack runs through the material. If the fracture had genuinely ended the project, the work should stop right at that line. It doesn't. Whoever was doing this kept going for some distance afterward, and the marks in that later section show no drop in quality whatsoever. Same curves, same spacing, same unsettling precision, even in the tightest, most physically awkward sections near the base. So if the crack didn't stop the work, something else did. And history, as of right now, has no clear answer for what that something was. If this ended at one location, you could reasonably file it away as a strange local anomaly. It doesn't end there. When researchers ran comparative analysis against granite structures at other well-known ancient sites, including some of the most puzzling stonework associated with later monumental complexes, the same underlying signature appeared again. The same sheer boundaries, the same faint rotational striations, the same overall cutting fingerprint. The measured variation between these separate, geographically distant sites came in under a narrow single-digit percentage. Combining the full data set, Grok AI reached a conclusion sitting around the high 80s in confidence. This pattern doesn't represent one isolated site or one gifted team of workers. It represents a shared method, used consistently across a wide region. A single skilled workshop is easy to explain. Passed down technique among a handful of master craftsmen, sure, that's plausible, but an identical, highly specific fingerprint appearing on different stone, hundreds of kilometers apart, with almost no variation between the two. That's not a workshop. That's a shared standard. The kind of consistency you only see when an entire civilization is operating from the same playbook. And somehow, that playbook disappeared so completely that for generations we assumed it never existed at all. There's one more wrinkle in this cross-site comparison that's easy to miss on a first pass through the data. When researchers looked specifically at sites separated by significant distance, and as far as anyone can tell, no direct trade or communication route connecting them, the shared fingerprint didn't weaken the way you'd expect it to. If this technique had spread the ordinary way, passed from teacher to student, workshop to workshop, gradually drifting and adapting as it moved, you'd expect small variations to creep in over distance, the way accents shift as language spreads across a region. Instead, the signature stayed remarkably stable, no matter how far apart the sites were. That stability is strange on its own terms. Human knowledge, passed by word of mouth and hands-on training across generations, tends to drift. Details get lost, methods get simplified or reinterpreted. The fact that this one didn't, that it shows up looking almost identical whether you're standing at one site or another hundreds of kilometers away, suggests either an extraordinarily rigid system of technical training we have zero historical record of, or a point of origin so singular and so well preserved in its transmission that it left no room for the kind of natural variation we'd expect from ordinary teaching. So here's where all of this actually leaves us. If the earliest work really is the most advanced, what happens to the comfortable assumption that technology only ever moves in one direction, forward? That single question undermines a lot of what we think we know, not just about this site, but but about how we assume history works in general. The pounding stone theory has been tested directly, and it did not hold up. Nobody has managed to physically reproduce marks that resemble what's actually carved into this stone using the tools history insists were available. That's not a small gap in the story. That's the center of it. Maybe the honest answer is that our historical timeline has a missing chapter we haven't located yet. Maybe some of the dating is off in ways we don't currently understand. Or maybe, and this is the possibility that keeps researchers up at night, the answer is something the field isn't fully ready to say out loud yet. Whatever the real explanation turns out to be, the stone itself isn't waiting for us to catch up. The marks are still there, exactly as precise as they've always been, and they're not asking the old story for permission anymore. It's worth remembering, too, that skepticism cuts both ways here. It's easy to get swept up in a single striking number and treat it as proof of something enormous. It's just as important to remember that one analysis, however careful, is a starting point for more research, not a final verdict. The honest position is the uncomfortable one in the middle. The accepted explanation clearly doesn't fit the evidence as well as we've been told for 100 years, and yet we still don't have a replacement explanation solid enough to replace it outright. That gap, sitting open and unresolved, is exactly why this story refuses to go away. So I want to know what you think. Lost technology nobody's documented, a dating error nobody's caught yet, or something we genuinely don't have a name for? Tell me in the comments. I read every single one, and honestly, some of the best theories on this channel have come directly from you. And if you think history is still holding back more than it's telling us, subscribe and turn on notifications so you're here the moment the next piece of this gets uncovered.